Hello everyone. In this video, we will learn to solve some problems related to equilibrium constant expression, both in terms of concentrations and pressures, and to determine the direction of reaction using the initial concentrations and calculating the reaction quotient of the reaction. Let's get started. The first example is about setting up the equilibrium constant expressions for a given reaction. Question: write the equilibrium constant expression for each of the following reactions. Reaction 1, we have 2 moles of sulfur dioxide reacting with 1 mole of oxygen gas to form 2 moles of sulfur trioxide gas. We learned earlier that equilibrium constant for a given chemical reaction is equal to the equilibrium concentration of products raised to the power of their stoichiometric coefficients divided by the equilibrium concentration of reactants raised to the power of their stoichiometric coefficients. So, for this reaction, the equilibrium constant K is equals to the concentration of products, that is sulfur trioxide, raised to the power of its stoichiometric coefficient, which is 2, divided by the concentration of the reactants, which is sulfur dioxide, to the power 2, and oxygen gas to the power 1. This is the equilibrium constant expression for the above reaction in terms of concentrations. Let us go to the next reaction. 1 mole of phosphorus pentachloride dissociates to give 1 mole of phosphorus trichloride and 1 mole of chlorine gas. For this, the equilibrium constant K is equals to the products of the reaction, that is concentration of PCl3 raised to the power of its coefficient 1 times concentration of chlorine to the power of its coefficient 1 divided by the reactants, that is the concentration of PCl5 raised to the power 1. Next, 1 mole of carbon dioxide gas reacts with 1 mole of solid carbon to form 2 moles of carbon monoxide gas. For this reaction, the equilibrium constant K is equals to the concentration of carbon monoxide to the power 2 divided by concentration of carbon times concentration of carbon dioxide. Note that this is an example of a heterogeneous equilibrium, that is, the reactants and products of the reaction are in different phases. We learned earlier that the concentration of pure solids and liquids are independent of the amount of the substance. That is, they are always constants. Therefore, we don't represent them in the equilibrium constant expression, which means the concentration of solid carbon won't show up in the equilibrium constant expression. So, the simplified equilibrium constant K is equals to the concentration of carbon monoxide power 2 divided by concentration of carbon dioxide. Let us now do an example problem converting Kc and Kp, that is, the equilibrium constant in terms of concentrations, to the equilibrium constant in terms of partial pressures. The question is, find the Kp of the following reaction if the equilibrium concentrations of PCl5, PCl3 and Cl2 at 450 Kelvin are 1.52 molar, 1.72 molar and 1.71 molar respectively. And the equation is 1 mole of phosphorus pentachloride decomposes to give 1 mole of phosphorus trichloride and 1 mole of chlorine gas. The equilibrium concentrations of all the reactants and products are already given in the problem. We can use them to calculate the equilibrium constant in terms of concentrations, that is Kc. For this reaction, equilibrium constant Kc is equals to the concentration of products, that is concentration of PCl3 power 1 times the concentration of Cl2 power 1 divided by the concentration of reactants, that is the concentration of PCl5 power 1. All these concentrations are at equilibrium. Let us plug in the equilibrium concentrations of all the reactants and products given in the problem. The concentration of phosphorus trichloride is 1.72 molar times concentration of Cl2 is 1.71 molar divided by the concentration of phosphorus pentachloride is 1.52 molar. If we do the math, we get the equilibrium constant in terms of concentrations Kc is equal to 1.94. Let us now calculate the equilibrium constant Kp from Kc. First, let me set up the equilibrium constant expression Kp. Kp is equal to the partial pressure of PCl3 times the partial pressure of Cl2 divided by the partial pressure of PCl5. Let us now derive a relation between Kc and Kp. We use the ideal gas equation to do that. We know that PV is equals to nRT. If we divide both sides of the equation with volume, we get pressure P is equals to N over V times RT. And N over V can be replaced with the concentration term in the above equation. So we get pressure P is equals to concentration times RT. Let us now take the equilibrium constant expression Kp and replace each partial pressure term in the equation by concentration times RT. The equilibrium constant Kp is equals to the concentration of PCl3 times RT times the concentration of Cl2 times RT divided by the concentration of PCl5 times RT. One RT and the other RT gets cancelled, and the concentration of PCl3 times concentration of Cl2 divided by the concentration of PCl5 can be replaced with Kc, which is equilibrium constant in terms of concentrations. So we get Kp is equals to Kc times RT. Let us now plug in the values of Kc, R and T in the above equation and calculate Kp. So Kp is equal to Kc, which is 1.94 times R. We know that R has different values. Since the partial pressures are expressed in atmospheres, I'm going to use R as 0.0821 liter atmosphere per mole Kelvin times the temperature is 450 Kelvin. If we do the math, we get Kp is equals to 71.63. This is how we calculate the relation between Kp and Kc. Example 3. Consider a hypothetical reaction A plus 3B gives 2C. The equilibrium constant for this reaction at 300 degrees Celsius is 3.0. Suppose we start the reaction with following concentrations, that is, concentration of A is 1 molar, concentration of B is 1 molar, and C also 1 molar. When the reaction starts, we need to pick one of the options. The forward reactions is faster and the reaction moves to right to reach equilibrium. Option B, the reverse reaction is faster and the reaction moves to left to reach equilibrium. Option C, rate of forward reaction is equal to the rate of reverse reaction. So, to determine which reaction is faster at the given time, we need to calculate the reaction quotient with initial concentrations given and compare it with the equilibrium constant K. The reaction quotient Q for the above chemical equation can be written as the concentration of C to the power 2 divided by concentration of A to the power 1 times concentration of B to the power 3. Note that these are not equilibrium concentrations. They could be any concentrations. Now, let us plug in the initial concentrations of reactants and products and solve for Q. The initial concentration of C is 1 molar divided by the initial concentration of A is also 1 molar times the initial concentration of B also 1 molar. If we do the math, we get 1.0. So, for the given concentrations, Q is not equal to K, which means that the reaction is not at equilibrium. And as we discussed earlier, a reaction always moves towards equilibrium. Let us try to visualize this. On the left-hand side, we have 100% reactants and 0% products. If we calculate the Q at this stage, we get Q is equals to 0. On the extreme right-hand side, we have 0% reactants and 100% products. If we calculate Q at this stage, we get Q would be equal to infinity. K for this reaction is given as 3. That means K is closer towards the 100% reactant side. Let me represent that somewhere here. K is equals to 3. The value of the reaction quotient that we calculated is 1. That means the reaction position is somewhere between the equilibrium position and the 100% reactance position. So let me represent it here. Q is equals to 1. In this case, Q is less than K. And we know that the value of equilibrium constant for a given reaction at a particular temperature always remains constant. Therefore, the value of Q should increase until it becomes equal to the value of K. Since Q describes the ratio of products to the reactants, that is, the products are in the numerator and the reactants are in the denominator, to increase the value of Q, the concentration of products, that is numerator, must increase and the concentration of reactants, that is denominator, must decrease. Which means the rate of the forward reaction must be faster than the rate of the reverse reaction, and the reaction overall moves towards the right hand side to reach equilibrium. So the correct option is option A.